call this home, our world.
You think
But
this
how
planet,
big is our world,
our
really,
planet,
when set against the
is big?
universe?
A vast, sprawling landscape where entire civilizations rise and fall, where oceans stretch beyond the horizon? What if I told you that in the grand cosmic scheme, Earth is less than a speck, a single grain of sand on an infinite beach? Today, we're not just looking at the universe, we're hunting its true monsters. And by the end of this journey, your perception of big will be shattered forever. Right now, you're standing on a world teeming with life, a vibrant blue marble, so familiar. It feels immense, doesn't it? Oceans that swallow entire continents, mountain ranges that scrape the sky. For millennia, this was our entire universe, our grand stage. We built empires, wrote symphonies, dreamt of the stars, all from this seemingly boundless home. But let's play a game. Let's shrink it. Imagine Earth, our magnificent home, reduced to the size of a single gleaming marble. Now, meet the undisputed king of our solar system, the gas giant Jupiter. If Earth is a marble, Jupiter is a basketball. You could cram over 1,300 Earths inside its swirling, stormy atmosphere. It's a behemoth, a gravitational bully, flinging comets around like cosmic slingshots. For a long time, Jupiter represented the absolute peak of planetary scale, a staggering reminder of how small we really are. But even Jupiter, even this colossal world, is just a warm-up act. Because then, you encounter the star, our star, the Sun, the very heart of our solar system, the furnace that fuels all life on Earth. If Jupiter is a basketball, then our Sun is a massive inflatable beach ball, maybe 10 feet across. You could fit 1,000,000 Earths inside it and still have room for a few Jupiters. It's a thermonuclear powerhouse, burning with an intensity that boggles the mind, a relentless fusion reactor that has shone for billions of years. For us, the Sun is the ultimate giant, a constant blazing presence that dominates our sky. It is, to our eyes, immeasurably vast. But here's the thing about the universe. It has a wicked sense of humor when it comes to scale. Just when you think you've grasped the meaning of huge, it pulls back the curtain on something that makes the Sun look like, well, a marble. Imagine our Sun. Now, imagine a star so colossal that if you placed it where our Sun is right now, its sheer bulk would swallow Mercury, Venus, Earth, Mars, and keep going. It would engulf Jupiter, obliterate Saturn's rings, and stretch out past Uranus, nearly reaching Neptune's orbit. Its outer edge would be where the farthest planets of our solar system currently reside. This isn't science fiction. This is Stevenson 2-18. Stevenson 2-18. The name itself sounds like something out of a deep space horror novel. It's a red hypergiant, one of the largest stars ever discovered, nestled in a stellar cluster nearly 12 light-years away. For years, astronomers grappled with the data, trying to comprehend its sheer scale. Dr. Emily Carter, a young astrophysicist on the team that refined its measurements, once described the moment they confirmed its radius. She said it was like looking at a blueprint for a god. She remembers feeling a chill, not just from the cold lab, but from the idea that something could exist with such impossible, terrifying dimensions. To give you a better sense, if you were to travel around the circumference of Stevenson 2-18, even at the speed of light, it would take you about 9 hours. 9 hours. To travel around a single star. Our Sun, by comparison, you could zip around in about 14 seconds. This isn't just a big star. This is a cosmic monster, a stellar behemoth that warps our understanding of what a star can be. It's so immense, Its own gravity is constantly fighting to pull it in, but its internal nuclear furnace is so powerful, it pushes back with an equal terrifying force. It's a dance of titans, a battle between creation and collapse, on a scale that beggars belief. But the universe, dear viewer, is never content with mere stars. Even the most gargantuan, light-blazing suns have a final act. And sometimes that final act is not a gentle fade, but a cataclysmic implosion, leading to something even more utterly, incomprehensibly monstrous. We're talking about black holes, the ultimate cosmic predators, places where gravity has become so absolute, so tyrannical, that nothing, not even light itself, can escape. We used to think of them as rare, exotic curiosities, but we've come to understand that every galaxy, including our own, harbors a secret, a deep, dark heart. Right at the center of our magnificent Milky Way galaxy, an object known as Sagittarius A star, or SGR-AU, quietly lurks. It's a supermassive black hole, 4 million times the mass of our Sun. Think about that for a second. 4 million suns, crushed down into a space smaller than our own solar system. It's the gravitational anchor for billions of stars, including our own, holding our entire galaxy together in a cosmic embrace. It's powerful, it's mysterious, and for a long time, SGR-A was the biggest, baddest black hole we knew. A cosmic monster of epic proportions, but just like with stars, the universe has a way of showing you that even your biggest monsters have bigger, scarier cousins. Imagine SGR-AU. Now, imagine a black hole so vast, so unfathomably massive, that SGR-AU would be a mere dust motes swirling around it. A black hole so immense that if you replaced our Sun with it, not only would it swallow our entire solar system, its event horizon, the point of no return, would extend beyond the orbit of Neptune, maybe even out to the Kuiper belt. It would gulp down planets, stars, entire stellar systems without a second thought. This is TON 618. TON 618 isn't just a black hole, it's an ultramassive black hole. A cosmic leviathan. It clocks in at an estimated 66 billion times the mass of our Sun. Billions, not millions. Billions. It defies comprehension. Scientists like Dr. Elena Petrova, who dedicated her career to studying quasars like the one TON 618 powers, describe it with a mix of scientific rigor and sheer unadulterated awe. She once said, "Quote, it's like looking into the eyes of a god and finding it utterly terrifyingly indifferent." TON 618 isn't just sitting there. It's an active galactic nucleus, a quasar, devouring everything around it and spewing out jets of plasma that stretch for hundreds of thousands of light years, brighter than 1,000 galaxies combined. It's a beacon of destruction, visible across vast cosmic distances, a testament to the universe's most extreme forces. Think about the implications. Our entire solar system, with its 8 planets, its asteroid belts, its comets, all the space from the Sun out to the farthest reaches of the Kuiper belt, that entire immense volume of space could orbit TON 618 like a tiny, insignificant ring of dust around a colossal, invisible king. Our Sun itself would be less than a single atom in a human body compared to the scale of this monster. It's not just big, it's a fundamental break from our earthly understanding of size, power, and even reality. It's a place where the rules we know simply cease to apply, where time and space are twisted into unimaginable knots. This is the infinite hunt, isn't it? A journey from the familiar comfort of our blue planet to the terrifying majesty of Stevenson 213, and then into the unimaginable maw of TON 618. These are the true monsters of the cosmos, not lurking under beds, but holding galaxies in their gravitational grip. burning brighter than 1 trillion suns, or swallowing entire systems whole. They are the ultimate giants, the cosmic leviathans that stand as silent, terrifying monuments to the universe's capacity for the extreme. And we are here, tiny, curious observers, perched on our speck of dust, reaching out across the unfathomable distances, piecing together the story of these titans. We are fortunate, perhaps even blessed, to glimpse these cosmic horrors, to feel the profound insignificance they impose upon us, yet still yearn to understand them, to name them, to measure them, to face them. But here's the most unsettling thought. Ton 618, as vast and terrifying as it is just one monster, a single colossal entity in a universe that is, by all accounts, infinite. What else could be out there? What other impossible reality-bending behemoths are still lurking in the cosmic shadows, waiting to be discovered? What other nightmares and wonders are yet to reveal themselves, ready to shatter our perception of the universes all over again? We've faced the giants. We've stared into the abyss of Ton 618, that impossible maw of gravitational hunger, a monster so vast, it warps our very understanding of scale. We've journeyed to Stephenson 2-18, a stellar leviathan that could swallow our entire inner solar system without a burp. These are the cosmic behemoths, the titans that define the absolute limits of size and power in our universe. But here's the most profound question, isn't it? Where did they come from? Where did anything come from? Before the stars, before the galaxies, before even the atoms that make up our bodies, there had to be a beginning, a genesis, a primal act of creation. To truly understand the monsters, we have to journey back, not just billions of years, but to the very edge of time itself, to a moment so mind-bendingly, profoundly alien, it defies our everyday experience. Forget planets, forget stars, forget even particles. We're talking about a universe smaller than an atom, a universe that was, in essence, all of existence, compressed into an infinitely dense, infinitely hot point. This wasn't just a tiny space. It was all space, and time itself. It hadn't even found its footing yet. Imagine, if you can, the unimaginable. The universe, in its infancy, was not a quiet dawn. Oh no. It was a scream, a primordial scream, of pure energy, erupting from nothingness, with a force that defies every law we now understand. The Big Bang. It's a terrible name, really. It wasn't a bang in space. It was the explosive expansion of space itself. Everything we see, everything we are, sprang from this one incomprehensible event. And it happened everywhere, all at once. There was no center to this explosion, because there was no outside to explode into. For the briefest fraction of a second, a blink so fast, it makes a nanosecond feel like an eternity, the universe went through a period of unimaginable inflation. It stretched and ballooned, growing from subatomic scale to macroscopic scale in less time than it takes light to cross a proton. Think of it like blowing up a balloon, but the surface of the balloon isn't just expanding, it is the universe itself. This rapid expansion smoothed out any wrinkles, flattening space, setting the stage for everything that would follow. It's a concept so wild, so counterintuitive, that when cosmologists first proposed it, they were met with serious skepticism. But the evidence, subtle yet profound, has since piled up, and then the universe began to cool, ever so slightly. But still, it was a cosmic crucible, a superheated, swirling plasma of fundamental particles, quarks, electrons, neutrinos, a chaotic energetic soup where matter and antimatter annihilated each other in a furious dance, leaving just a tiny excess of matter behind. Thank goodness for that excess. Otherwise, There'd be no us, no stars, no universe, just an empty sea of light. This was a universe opaque. Light couldn't travel freely. It was constantly being absorbed and re-emitted by the charged particles trapped in this brilliant, blinding fog. Imagine standing inside the heart of a star, but everywhere you look, there's nothing but blinding light, no direction, no shadow, just pure, unadulterated energy. This was the universe for its first few 100,000 years. A fiery, frantic baby, still too hot and dense to even form a stable atom. But as the universe continued its inexorable expansion, it continued to cool. And as it cooled, the fundamental particles finally found a moment of peace. Protons and neutrons, forged in the first few minutes, began to combine. Simple, elegant, yet utterly profound. They fused, driven by the intense heat and pressure, to create the very first elements, hydrogen, proton, and helium, POO. These weren't just some of the ingredients. They were, by far, most of them. About 75% hydrogen, 25% helium, with a tiny trace of lithium. These two humble elements, born in the first few moments after the Big Bang, are the key raw ingredients for absolutely everything that exists today. Every star, every planet, every living thing, including you and me, we are all ultimately made from the ashes of that primordial fire. Then came a pivotal moment, about 380,000 years after the Big Bang. The universe had cooled enough, finally, for electrons to settle down and combine with those patiently waiting hydrogen and helium nuclei. For the first time, stable neutral atoms could form. This event, known as recombination, was literally when the lights came on. The universe suddenly became transparent. The photons, the particles of light that had been trapped for eons, were finally free to travel. They streamed out in every direction, an ancient echo of that fiery birth. And we can still hear that echo today. It's the cosmic microwave background, or CMB, the faint uniform glow of microwave radiation that permeates the entire sky. It's the universe's baby picture, taken at 380,000 years old. When Arno Penzias and Robert Wilson accidentally discovered it in 1964, they initially thought it was pigeon poop, interfering with their antenna. Can you imagine the frustration? Then the sheer mind-bending awe when they realized they had stumbled upon the literal afterglow of creation. It was the definitive proof of the Big Bang, a cosmic fingerprint, printed across the very fabric of space. But don't let that light fool you. After recombination, a new era dawned, the height of cosmic dark ages. This wasn't a period of fiery chaos, but of profound, almost terrifying emptiness. The universe was now transparent, but it was also cold, vast, and utterly devoid of anything we would recognize as light. There were no stars, no galaxies, just an expanding ocean of neutral hydrogen and helium gas, gently cooling, stretching out into the cosmic void. Imagine a universe cloaked in an eternal silent night. No suns to warm it, no nebulae to illuminate it, just the uniform faint whisper of the CMB, fading into the background. It was a period of immense mystery, lasting for hundreds of millions of years. What was happening during that time? How did this vast, empty expanse, filled only with simple gas, give rise to the complexity we see today? The answer lies in the subtle, unseen forces at play. Dark matter, that elusive, invisible scaffolding of the cosmos, began to coalesce. Its gravitational pull, though gentle, started to draw in the hydrogen and helium gas, forming vast, invisible clumps and filaments. Slowly, agonizingly, gravity began its work, gathering the raw materials, preparing the stage for the next great act of creation. And then finally, After hundreds of millions of years of waiting, the pressure and density within those dark matter clumps became so immense that the gas within them ignited. The first stars were born. These weren't like our sun. Oh no. These were population 3 stars. True giants, hundreds, even thousands of times more massive than our sun, burning with an almost unimaginable intensity. They lived fast and died young, exploding in cataclysmic supernovae that ripped apart the pristine hydrogen and helium, scattering heavier elements, carbon, oxygen, iron, throughout the nascent universe. These first stars were the universe's alchemists. They took the simple hydrogen and helium forged in the Big Bang, and in their fiery hearts and violent deaths, created the very first building blocks for everything else. Without them, there would be no rocky planets, no complex chemistry, no life. They were the true genesis of giants, the ancestors of the supermassive stars and black holes we marvel at today. Their lives were short, but their legacy, absolutely eternal. From a scream of pure energy, to a superheated plasma, to a vast, dark emptiness, and finally, to the first glorious pinpricks of starlight. This is the echo of creation. This is the story of how the very fabric of existence was woven, thread by thread. From the simplest ingredients, we've come a long way, from those impossible cosmic monsters, only to find that even they are children of this primal forge. They are the ultimate expression of what happens when these fundamental forces, these raw materials, are given billions of years to play out their cosmic dance. We too are part of that story, made from the same stardust, built upon the same fundamental laws. And as we gaze out at the universe, we're not just looking at stars and galaxies. We're looking at ourselves, reflected in the vast ancient mirror of time. But the universe wasn't done. Far from it. These first stars, these fledgling galaxies, they were just the beginning. The seeds had been planted. The stage was set. But what happened next? How did these early chaotic beginnings lead to the intricate, breathtaking cosmic tapestry we inhabit today? How did these simple elements organize themselves into the colossal structures that continue to amaze and terrify us? The universe, it seems, was just getting started. And its story, our story, was about to get truly wild. Imagine a universe just a few 100 million years old, not quite the dazzling canvas we see today. Instead, picture a vast, almost featureless cosmic fog. A universe filled with hydrogen and helium, swirling in a lukewarm, inky blackness. No stars, no galaxies, just the void. This was the cosmic dark ages, a period of profound stillness, where the universe held its breath, waiting for its first spark. It was a universe ripe with potential, yet utterly barren. A canvas painted in monochrome, stretching out for hundreds of millions of years, an epoch of silence and unyielding darkness. It's hard to wrap our minds around that kind of emptiness, that profound absence of light. Every direction you looked, for unimaginable distances, there was nothing but the faintest afterglow of the Big Bang, slowly fading into obscurity. The cosmos was a vast, cold nursery, waiting for its first cries. But even in that darkness, invisible forces were at play. Gravity, the silent sculptor of the cosmos, was beginning its work. It was tugging, ever so gently, at the densest pockets of gas. Think of it like slow, deliberate breaths, pulling together wisps of primordial hydrogen and helium. And here's where things get truly wild. It wasn't just ordinary matter doing the heavy lifting. The universe was secretly dominated by something we can't see, can't touch, can't even directly detect. Dark matter. This mysterious substance, making up about 27% of the universe's mass, acted as the universe's invisible scaffolding. These dark matter halos, like colossal ghostly clouds, provided the gravitational anchors. They were the enormous unseen cradles where the very first stars would be born. Without them, the diffuse gas would have simply spread out, never quite dense enough to ignite. Dark matter was the invisible hand, guiding the first aggregations of matter, whispering to the gas clouds, "Rouse, come closer. Collapse. Ignite." Oh, inside those halos, hydrogen and helium gas, compressed by unimaginable gravitational forces, began to heat up. The pressure, the density, it grew to a critical point. The gas clouds, hundreds of thousands of times the mass of our sun, continued to shrink, spinning faster, growing hotter. And then, about 100 to 200 million years after the Big Bang, it happened. The universe ignited. These weren't just any stars. These were the true trailblazers, the cosmic pioneers, the population 3 stars. And they were nothing like our sun, or any star we see commonly today. Imagine stars that were hundreds, even 1,000 times more massive than our own sun. Not just a little bigger, but truly gargantuan celestial monsters in their own right. Their cores burned with an intensity we can barely fathom, fueled by pure hydrogen and helium, the only elements available in that pristine early universe. Because they lacked any heavier elements, what astronomers called Rabault's metals, anything heavier than helium. Their internal physics were different. There was no carbon or oxygen to help cool the collapsing gas, allowing these nascent stars to grow to truly monstrous scales before nuclear fusion finally kicked in. They were born out of pure, unadulterated primordial gas. Pristine and perfect, these titans blazed with the luminosity of millions of suns. They were cosmic beacons, piercing the primordial darkness, radiating pure, unadulterated starlight for the very first time. You could say they were the universe's original first light, the dawn breaking after an eternity of night. Their light was a furious, ultraviolet torrent, far more energetic than anything our sun produces. They were the universe's first streetlights, illuminating tiny patches of the vast cosmic night, signaling that the long dark ages were finally coming to an end. It was a triumph of physics, a testament to gravity's power to overcome the void and bring forth incredible brilliance. But for all their brilliance, these giants lived fast and died young. Their immense mass meant they burned through their fuel at a furious, suicidal pace. Instead of billions of years, like our sun, these celestial behemoths survived for mere millions, a blink of an eye in cosmic time. Think about that. A star so powerful, so immense, that it exhausts its entire life's supply of fuel in less time than it took for dinosaurs to rule the Earth. It's an almost tragic beauty, a fleeting, spectacular existence. But in that brief, spectacular lifetime, they performed an alchemy that changed everything. Deep within their hearts, under pressures and temperatures beyond imagination, they began to fuse hydrogen and helium into something new, something heavier. Carbon, oxygen, nitrogen, iron, all the elements essential for planets, for life, for us. They were forged in the crucibles of these first stars. The oxygen you breathe, the carbon that forms the backbone of every organic molecule in your body, the iron in your blood, the silicone in your phone, the gold in your jewelry. Every single atom, heavier than helium, was once cooked in the heart of a star, or created in its explosive death. Every trace of these precious elements began its journey right here, in the cores of these colossal ancient suns. Without them, the universe would remain a sterile, lifeless expanse of hydrogen and helium. They were the universe's first element factories, laying down the fundamental chemistry for everything that would follow. And when their fuel ran out, these population 3 stars didn't just fade away. Oh no, they went out with a bang. A truly spectacular cataclysmic bang. Supernovae of unimaginable power, vastly more energetic than anything we observe today. These weren't just stellar explosions. They were cosmic fireworks that ripped themselves apart and scattered those newly forged heavy elements across the nascent universe. It was an act of cosmic generosity, seeding the void with the building blocks of everything that would follow. These supernovae also sent out powerful shockwaves, compressing the surrounding gas and dust, triggering new waves of star formation, creating a cascading effect that began to sculpt the cosmos. These stellar explosions, while destructive, were also incredibly creative. They sent shockwaves through the surrounding gas, compressing it further, initiating new cycles of star formation. And as more and more of these first stars ignited, lived and died within their dark matter halos, a new kind of structure began to emerge. Not just individual stars, but clusters of them, pulled together by their mutual gravity. These were the very first proto-galaxies. Think of them as tiny luminous islands in a vast dark sea, like seeds, scattered across the void, beginning to sprout. Imagine millions of these early, chaotic stellar nurseries, each one a frenzy of birth and death, blazing with the light of millions of young hot stars. The gravitational dance continued. Stars, gas, and dark matter, all pulling on each other, coalescing, merging. It was a slow, majestic ballet, playing out over hundreds of millions of years. These proto-galaxies weren't the grand spirals and ellipticals we see today. Oh no. They were clumpy, chaotic, and fiercely active, constantly forming new stars, constantly being reshaped by the gravitational forces of their neighbors. They devoured smaller clumps, grew larger, and started to resemble the embryonic versions of the magnificent galaxies that would eventually fill the universe. It was a period of intense cosmic growth, a universe in its tumultuous infancy, constantly building, constantly evolving. And here's another wow moment that astronomers are still piecing together, largely thanks to the incredible eyes of the James Webb Space Telescope. Remember that cosmic fog I mentioned? The one that shrouded the early universe in darkness? The light from these first stars and proto-galaxies was so powerful, so intense, that it began to burn off that fog. It ionized the neutral hydrogen gas, stripping electrons from their atoms, essentially making the universe transparent. This era, known as rionization, was a monumental turning point. For billions of years, the universe had been opaque, like looking through a thick haze, preventing light from traveling freely. But the sheer torrent of ultraviolet radiation from those first trailblazers literally cleared the way, allowing their distant descendants, stars and galaxies like our own, to shine brightly across the cosmos. It's a testament to the sheer power of light, overcoming the primordial darkness, transforming the universe from an unseeable shroud into the clear, luminous expanse we observe today. Imagine the universe itself holding its breath, waiting for this moment, for the veil to be lifted, for the first true glimpse of its own incredible beauty. Understanding this period, seeing first light, is one of the holy grails of modern astronomy. For decades, scientists like Richard Ellis, Volker Braun, and countless others have been sifting through faint signals, pushing the limits of our telescopes, trying to reconstruct this ancient history. It's a colossal cosmic detective story, where every flicker of light from a distant galaxy is a clue, every spectral line a fingerprint from the past. They've spent careers dreaming of this, of a telescope powerful enough to peer back into this critical epoch. The James Webb Space Telescope, for instance, isn't just taking pretty pictures. It's a true time machine. Its infrared eyes are designed to peer back through billions of years to directly observe these first nascent galaxies. Imagine the hope, the sheer exhilaration, the years of anticipation culminating in those first deep field images. The scientists, some of whom had dedicated their entire lives to this mission, watching those fuzzy, faint images coalesce into something tangible. Images showing galaxies so ancient, so incredibly far away, that the light reaching us today left them when the universe was just a baby. It's like finding the very first chapters of a cosmic novel, a story we thought we could only imagine, now laid bare before our eyes. It's a profound moment of human triumph, a testament to our insatiable curiosity and our ability to reach across billions of light years of space and time. So, what's the legacy of these colossal, short-lived pioneers? Everything. Without them, there would be no heavy elements, no carbon, no oxygen, no iron, no rocky planets, no life. They were the universe's first architects, using gravity and fusion to lay the foundations for all the complexity that followed. They carved out the first luminous structures, pulling gas and dust into their gravitational embrace, setting the stage for the magnificent galaxies that would eventually blossom. From these humble, chaotic beginnings, a universe of mostly hydrogen and helium, emerged the seeds of structure, the first stars, the first elements, the first proto-galaxies, each one a tiny triumph of light over darkness, a testament to the universe's relentless drive towards complexity, towards organization, towards life itself. And as these early galaxies grew, as billions upon billions of stars formed within them, something else began to stir, something even more profound, even more terrifyingly powerful. Because within the heart of almost every galaxy, including our own, lies an entity of unimaginable density and gravitational pull, an entity that began its growth quietly in those early cosmic nurseries. We've seen the universe create wonders of light and life, but it also creates monsters. And as these early structures evolved, as galaxies merged and grew, so too did these colossal, invisible titans. They are the ultimate cosmic predators, shaping galaxies, devouring stars, bending space-time itself. And they are, perhaps, the most extreme examples of the universe's capacity for scale. You think our planet is big. You think our sun is a behemoth. Prepare to feel infinitesimally small, because the universe, in its boundless creativity, didn't just stop at forming stars and galaxies. It went on to forge objects of such mind-bending scale, such terrifying power, that they challenge our very comprehension. We're talking about objects so vast, so dense, that they warp reality around them. The journey to the cosmic monsters has only just begun. And believe me, it gets far wilder from here. We've glimpsed the universe's most extreme examples of scale, those cosmic monsters that defy comprehension. We've seen titans of gravity, behemoths of pure energy, and objects so vast they bend reality. But where do these monsters live? Where do stars ignite, and planets coalesce, and life take root? They live in magnificent, sprawling cities of light, vast islands of stars we call galaxies. And we, my friends, live in one of the grandest of them all, the Milky Way. Think about it. We're here right now, on this pale blue dot, hurtling through space at over 500,000 miles an hour, not just around our sun, but around the center of our galaxy. But for most of human history, we didn't even know what a galaxy was. We certainly didn't know we lived in one. The hazy band of light across our night sky, we called it the Milky Way. Then a river of milk, a celestial pathway, a comforting cosmic blanket. We thought it was all there was. We were the center of a universe that seemed to fit neatly around us. Oh, how wrong we were. It took incredible ingenuity, persistence, and a healthy dose of defiance to break free of that limited view. Imagine the sheer, quiet dedication, day after day, year after year, hunched over photographic plates, meticulously measuring the tiny shifts of light from distant stars. That was the work of Henrietta Leavitt, a brilliant but unsung astronomer at the Harvard College Observatory in the early 20th century, in an era where women were often relegated to watch computers, meticulously analyzing data rather than forming theories. Leavitt found a pattern that would crack open the universe. She was studying a type of star called a Cepheid variable. These celestial beacons don't just shine, they pulse, they rhythmically brighten and dim. And Leavitt discovered their secret. The brighter a Cepheid intrinsically was, the slower it pulsed. A simple, elegant relationship. Suddenly, we had a cosmic yardstick. If you knew how bright a Cepheid truly was, and you could measure how bright it appeared from Earth, you could calculate its distance. It was a simple, elegant key to an unimaginable lock. Her name, for too long, remained a footnote in a scientific history dominated by men. But her contribution, it was monumental. She gave us the first true way to measure the vastness of space. But even with Leavitt's yardstick, the true scale of the universe remained shrouded in mystery. Was our Milky Way all there was? Or were those fuzzy, luminous patches we saw through our telescopes, those yellow spiral nebulae, actually other galaxies, other island universes far beyond our own? This was one of the greatest scientific debates of the early 20th century. It was like peering through a keyhole into a vast, uncharted ocean. And what would Edwin Hubble, using the most powerful eye on the sky at the time, the 100-inch Hooker telescope on Mount Wilson, find there? Hubble set his sights on the Andromeda Forstau Nebula Teot. And there, amidst the swirling gas, he found them, those pulsing Cepheid variables. He applied Leavitt's genius formula. And the numbers he got, they were staggering. Andromeda wasn't a cloud within our galaxy. It was millions of light-years away, 2.5 million light-years to be precise. Think about that. If you could travel at the speed of light, the fastest thing in the universe, it would still take you 2.5 million years to reach our nearest galactic neighbor. Would humanity even exist by the time you got there? Boom. The universe exploded. In that single glorious moment, our cosmic solitude was shattered. The Milky Way was just one of billions of galaxies, each a colossal empire of stars, spread across an unimaginable expanse. It was a moment that redefined our place in the cosmos, a realization that was both humbling and exhilarating. So, what does our galactic home, this Milky Way, truly look like from the outside? Picture a colossal cosmic frisbee, a sprawling spiral of stars, gas, and dust, spanning 100,000 light-years across. At its heart, a brilliant bulge, packed with ancient stars, glowing with the light of 1,000,000 suns. From that bulge, grand spiral arms unfurl, like a celestial pinwheel, each arm a stellar nursery, a highway of gas and dust, where new stars are constantly being born. We live, somewhat prosaically, in one of these arms, the Orion arm, about 2/3 of the way out from the galactic center. When you look up at the night sky and see that hazy band of light, the actual ultimate Milky Way, visible to your naked eye, you're not seeing stars outside our galaxy. You're looking right through the densest part of our home galaxy's disk, at countless stars too far away to resolve individually, their combined light creating that luminous river. These magnificent spiral arms, they're not like fixed spokes on a wheel. Stars actually move in and out of them. Think of it like a cosmic traffic jam, a density wave where gas and stars pile up, sparking new star formation. So the stars you see in an arm today might not be there in 1,000,000 years, but the arm itself persists, a swirling pattern etched into the fabric of space. It's a grand, slow-motion ballet, choreographed by gravity on the grandest stage imaginable. But our galaxy isn't just a flat disk. Surrounding it, in a vast spherical halo, are hundreds of ancient, tightly packed clusters of stars called globular clusters. These are some of the oldest structures in the universe, relics from the Milky Way's infancy, each one a miniature stellar city, home to hundreds of thousands of stars. They orbit our galaxy like loyal sentinels, silent witnesses to billions of years of cosmic history. As we started to map our galaxy, and indeed other galaxies, a troubling mystery emerged. When astronomers measured how fast stars were orbiting the galactic center, especially those far out in the spiral arms, they found something deeply unsettling. They were moving way too fast. Based on all the visible matter, the stars, the gas, the dust, these outer stars should have been flung off into intergalactic space, like marbles off a spinning merry-go-round. But they weren't. Something invisible, something enormous, was holding them in. Something was providing extra gravity. That something, we now believe, is dark matter. A cosmic ghost. It doesn't emit light. It doesn't absorb light. It doesn't reflect light. We can't see it. We can't touch it. We can't even directly detect it. Yet. But its gravitational influence is undeniable. Imagine trying to build a skyscraper without a foundation, without steel beams. It would collapse. Dark matter is the invisible scaffolding, the gravitational backbone that holds galaxies together. It's the cosmic glue that prevents our galactic empire from tearing itself apart. In fact, the visible matter, everything we can see, everything we're made of, every star, every planet, is just a tiny fraction of the total mass of our galaxy. The Milky Way, and indeed most galaxies, are utterly dominated by this unseen presence. It's a bizarre reality check, isn't it? That the very fabric holding our galactic home together, this magnificent spiral of billions of stars, is almost entirely made of something we can't see, can't touch, can't even truly comprehend. It's a humbling thought that most of our universe is utterly invisible to us. Galaxies aren't static sculptures, frozen in time. They're living, breathing entities, constantly interacting, growing, and even devouring each other. Our own Milky Way has likely consumed several smaller galaxies in its lifetime. They're stars now part of our grander structure, a testament to cosmic cannibalism. And in about 4.5 billion years, our galactic home is destined for a cosmic collision. Our nearest major neighbor, the Andromeda Galaxy, is hurtling towards us at 110 kilometers per second. Don't worry, you won't be around to see it. But when they meet, it won't be a head-on crash of stars. The distances between stars are so vast that actual stellar collisions will be incredibly rare. Instead, it'll be a slow, majestic dance, a gravitational embrace that will eventually merge our two spiral galaxies into one colossal elliptical galaxy, a new grander empire, forged from the collision of two. Imagine the view. And at the very heart of our Milky Way, lurking in the galactic center, is one of those cosmic monsters we hinted at earlier, Sagittarius A, pronounced A star, a supermassive black hole, 4 million times the mass of our Sun, quietly reigning over our galactic core. It's the ultimate gravitational anchor, keeping everything in its colossal orbit, a silent, all-consuming king at the center of our magnificent empire. So, here we are. Billions of stars, countless nebulae, ancient globular clusters, and an invisible shroud of dark matter, all swirling in a magnificent cosmic ballet. This is our home. This is the Milky Way. It's a place of incredible beauty, immense scale, and profound mystery. A testament to the universe's capacity for creating intricate, self-organizing structures. And the more we learn about it, the more we understand our tiny yet precious place within its grand design. We stand on a small blue planet, in a quiet corner of one of these spiral arms, and gaze out at a universe that is both terrifyingly vast and intimately connected. Every star you see with your naked eye, almost every object, is a part of this cosmic home. But our galaxy, as immense as it is just one of billions, and the space between them, that vast dark canvas, holds even more secrets, even more scale, even more emptiness. What fills that void? And what happens when galaxies aren't just merging, but being pulled apart by an even greater unseen force? The journey, my friends, always continues, and the universe has even grander, more chilling revelations waiting for us just beyond the edge of our own galactic empire. We've peered into the abyss. We've felt the chill of intergalactic voids and marveled at galaxies locked in a slow cosmic dance. We've chased the monstrous shadows of black holes and stood in awe of stars so vast they defy imagination. But what if the most profound mystery, the most incredible story isn't out there, in the cosmic wilds? What if it's right here beneath our feet? Because for all the monsters and marvels of the universe, there's one place, one tiny improbable speck, that truly holds our hearts, our home. Look down, feel the ground beneath you, the solid, unwavering earth. It feels permanent, doesn't it? Like it's always been here, always will be. But our planet, this vibrant, living world, is not eternal. It had a beginning, a violent, chaotic, utterly astounding birth. And understanding that birth, that journey from cosmic dust to a living, breathing world, isn't just a scientific pursuit. It's a profound act of self-discovery. It's how we find our true place in the grand cosmic narrative. Imagine, if you will, 4.5 billion years ago. Forget the tranquil blue marble you know. Our solar system was nothing but a colossal swirling cloud of gas and dust, a nebula stretching light years across, a cosmic junkyard of hydrogen, helium, and heavier elements forged in the hearts of long-dead stars. It was a dark, cold, seemingly featureless expanse, but within that quiet darkness, something was stirring. A subtle ripple, perhaps the shock wave from a nearby supernova, disturbed the gas cloud. A tiny imbalance. And that tiny imbalance, my friends, was the spark. Gravity, the universe's tireless sculptor, began its work. Particles, ever so slightly closer together, pulled on their neighbors. Slowly, inexorably, the cloud started to collapse inward, picking up speed, like a cosmic whirlpool. As it spun faster, it flattened into a colossal disk, thinner at the edges, bulging at the center. Think of a pizza dough being tossed by a giant chef, spinning and spreading out. In the heart of that disk, the pressure and temperature soared, igniting the fusion furnace that would become our sun. A star finally roaring to life. But what about us? What about the planets? They were born from the leftover debris in that spinning disk. Imagine countless microscopic grains of cosmic dust, like tiny ball bearings, gently bumping into each other. Most of these collisions were soft, sticky. They started to clump. Dust bunnies grew into pebbles, pebbles into rocks, rocks into boulders. This process, called accretion, wasn't always gentle. It was a demolition derby on an epic scale. Early planetesimals, some hundreds of miles across, smashed into each other with terrifying force, shattering, merging, growing. It was a cosmic construction site, loud and violent, where mountains of rock were formed in fiery impacts. For hundreds of millions of years, this brutal ballet continued, until eventually, a few massive bodies emerged from the chaos, our planets, and among them, a particularly fortunate one, roughly a third of the way out, from the newborn sun, our Earth. But this early Earth was no paradise. It was a molten hellscape, constantly bombarded by asteroids and comets, its surface a sea of bubbling rock. Then came an impact that would forever define our world. a Mars-sized protoplanet, now known as Theia, slammed into our nascent Earth. An impact so cataclysmic it would have vaporized oceans, melted continents. The debris from this titanic collision, flung into orbit, eventually coalesced to form our moon. A moon that is disproportionately large for its planet, an ancient cosmic twin, forever bound to us. And this moon, born of violence, became one of the unsung heroes in the story of life. Its immense gravitational pull stabilized our young planet's tilt, preventing wild, chaotic wobbles that could have plunged us into extreme ice ages or scorching infernos. It gave us stable seasons, a predictable rhythm. It also created the tides, stirring the primordial oceans, mixing chemicals, perhaps even helping to kickstart the very first life. Without our moon, our pale blue dot might have been a very different, far less hospitable place. But the moon wasn't alone in its cosmic guardianship. Farther out, a true behemoth was forming. Jupiter. You might think of Jupiter as just a pretty gas giant with a big red spot. But it's more than that. Jupiter is our solar system's cosmic bodyguard. Its immense gravity acts like a giant broom, sweeping up or deflecting countless asteroids and comets that might otherwise have smashed into the inner planets, including Earth. It's not perfect, of course. We still get hit. But without Jupiter, our planet would have faced a bombardment so relentless, so destructive, that life as we know it might never have had a chance to take root, let alone flourish. And then there's the address, the perfect address. We call it the Goldilocks zone. Not too hot, not too cold. Just right. Earth orbits the sun at precisely the right distance for liquid water to exist on its surface. Not frozen solid, not boiled away into vapor, but flowing, life-giving liquid water. Scientists like Dr. Jill Tarter, who dedicated her life to the search for extraterrestrial intelligence, often remind us that water isn't just a convenience for life. It's the fundamental solvent, the medium for the complex chemistry that is life. Without it, the story ends before it even begins. But even with water, even with a stable tilt and a cosmic bodyguard, Earth still needed more. It needed an atmosphere. It needed a magnetic field. Our planet's churning liquid iron core generates a powerful magnetic field that wraps around us like an invisible shield. This magnetosphere deflects the sun's deadly solar winds, a constant stream of charged particles that would otherwise strip away our atmosphere and irradiate our surface. It's why we have the stunning aurora borealis and australis, those cosmic light shows at our poles, a beautiful side effect of our planet defending life. And the atmosphere itself, a complex blend of nitrogen, oxygen, and other gases, painstakingly built up over billions of years. Early Earth's atmosphere was toxic to us, rich in volcanic gases. But then, single-celled organisms, the pioneers of photosynthesis, began to transform it. They breathed in carbon dioxide and exhaled oxygen, slowly, painstakingly, terraforming our entire planet, creating the breathable air that allows us to exist, to laugh, to dream. It's an almost unbelievable chain of events, isn't it? A colossal gas cloud, a stellar ignition, a violent cosmic demolition derby, a catastrophic impact, the steadying hand of a massive moon, the protective shield of a gas giant, the perfect orbital address, an invisible magnetic force field, and the patient, planet-altering work of microscopic life. Each step, each condition, so finely tuned, so improbable. This isn't just a collection of scientific facts. It's our origin story. It's a testament to the sheer mind-boggling improbability of our existence. When we look at the hostile environments of our cosmic neighbors, the searing heat of Venus, the frozen desolation of Mars, the crushing pressures of the gas giants, we begin to grasp the sheer fragile miracle that is Earth. We are not just living on a planet. We are living on a masterpiece, a cosmic jewel polished by billions of years of trial and error, of destruction and creation. The scientists who piece together this incredible narrative, people like Dr. Carolyn Porco, who has spent her career studying the outer planets, or Dr. David Catling, who models early Earth atmospheres, are more than just researchers. They are cosmic detectives, patiently sifting through geological records, analyzing ancient meteorites, and meticulously modeling planetary dynamics. They are the ones who translate the whispers of the universe into a language we can understand, revealing our planetary ancestry, showing us how we came to be. Their work is a labor of love, driven by an insatiable curiosity, a desire to know not just what happened, but how this incredible story unfolded. And as we stand on this pale blue dot, gazing out at the vastness, we are filled with a profound sense of gratitude. Gratitude for the improbable luck that led to this home. Gratitude for the delicate balance that sustains us. Gratitude for the sheer resilient tenacity of life itself. We are vulnerable, yes, a tiny oasis in an infinite desert. But we are also connected. Every atom in your body, every breath you take, every landscape you admire, is a direct consequence of this cosmic journey. We are literally stardust, made of the same stuff that forged the sun and the planets, brought together in this incredibly precise way to form something truly extraordinary. This planet, our Earth, isn't just a rock we live on. It is a living, breathing entity, a cradle of worlds, delicately balanced, profoundly precious. It is our past, our present, and our future. And understanding its genesis, understanding our connection to the cosmic forces that shaped it, isn't just knowledge, it's a call to action. A reminder of what we have, what we stand to lose, and the incredible responsibility we bear. But what if, out there, in that vast, star-strewn darkness, other cradles exist, other pale blue dots, orbiting other suns, nurturing other forms of life? The universe is immense, full of possibilities, and the search for answers to that question, the quest for cosmic company, is perhaps the greatest adventure humanity has ever embarked upon. The next chapter in our story begins with a listen. Listen. It's a beautiful thing, isn't it? To tune into the cosmic symphony, to hear the echoes of the Big Bang, the whispers of alien worlds. But sometimes, to truly grasp the universe, you don't just need to listen. You need to see it. And what we're about to see, well, it might just make your jaw drop. You think our Earth is vast, a majestic blue marble, teeming with life, stretching out in every direction, a boundless horizon. It is. From our perspective, it's home. It's everything. But hold on tight, because today, we're going monster hunting. We're going to confront the true titans of the cosmos, the giants that make our home, our sun, our entire solar system, shrink to an almost embarrassing speck. To understand true scale, we have to start small. Well, small-ish. Imagine Earth. Now picture Jupiter, the king of our solar system. You could cram over 1,300 Earths inside its swirling, gaseous embrace. That's already mind-boggling, right? A planet so massive, it almost feels like a star. Almost? Because even Jupiter is just a cosmic pebble compared to our sun, the heart of our solar system. A colossal furnace, burning with the power of 1,000,000 nuclear bombs every second, giving life to everything we know. You could fit 1,000,000 Earths inside it. 1,000,000. For most of human history, this star, our star, was the biggest, most powerful, most terrifyingly large object we could even conceive of. It was the ultimate cosmic behemoth. But out there, in the cosmic wilds, our sun is barely a toddler, a cosmic pebble, a backyard firefly. We're about to meet the true giants, the Goliaths that make our star look like a speck of dust. Welcome to the realm of stellar kings. We call them hypergiants, red hypergiants, and their names, like Stevenson 218 or UI Scuti, sound almost mundane. But their reality, it's anything but. Imagine taking our sun, shrinking it down to the size of a tiny marble. Now, imagine Stevenson 218. If our sun is that marble, Stevenson 218 is a sphere so vast it would dwarf a skyscraper. No, that's not enough. It would be the size of a small moon. No, even that fails to capture the scale. If you were to swap out our familiar sun for Stevenson 218, its fiery, bloated surface would reach out past the orbit of Jupiter, past the orbit of Saturn. Some estimates even put it reaching past Uranus, maybe even Neptune. Think about that for a second. Our entire solar system, the familiar dance of planets we've charted and studied for centuries, would be completely swallowed whole. Mercury, Venus, Earth, Mars, Jupiter, Saturn, all vaporized, lost within its incomprehensibly vast, crimson embrace. The orbits our worlds have traced for billions of years would simply cease to exist, absorbed into the heart of this monster. It's a scale so immense, our brains simply aren't wired to comprehend it. We try with analogies. If the sun were a grain of sand, UI Scuti would be a beach ball. But even those break down, because the reality is so much more extreme. These aren't just big, they are bloated. Imagine a star that's lived so fast, burned so intensely, that it's expanded outwards, shedding its outer layers like a cosmic onion, growing to an almost impossible size. They live on the edge, consuming their fuel at an insane, furious rate, burning through billions of years of energy in mere millions. They are the rock stars of the cosmos, live fast, die young, and leave behind a huge, beautiful, terrifying corpse. And when these giants die, oh, do they go out with a bang. A supernova, an explosion so powerful it can briefly outshine an entire galaxy, a collection of hundreds of billions of stars, for a brief, glorious moment. It's the universe's most spectacular, most violent fireworks display. But it's also a cosmic funeral pyre, the death throes of a true monster. But the story doesn't always end there. For the most massive stars, the ones that truly push the boundaries of existence, what's left behind is something even stranger, even more extreme, something that defies our everyday understanding of matter. After the supernova blast rips away the outer layers, the core, if it's massive enough, doesn't just fade away. It collapses, implodes. With a gravitational force so intense, it crushes every atom out of existence. What remains? A neutron star. Picture this. A star, many times more massive than our sun, collapses down to the size of a city. A single city. All that mass, all that gravity, squeezed into a sphere just 20 kilometers across. If you took just a spoonful of neutron star material, it would weigh billions of tons, more than every car on Earth combined. It's so dense, so incredibly compact, that the electrons and protons within its atoms have been crushed together, forcing them to become neutrons. It's a literal atomic soup, a cosmic diamond born from stellar death. And these aren't inert objects. Many neutron stars spin incredibly fast, some rotating hundreds of times per second, beaming out powerful radiation like cosmic lighthouses. We call them pulsars. They are the ticking clocks of the universe, silent, relentless, terrifyingly precise. Imagine standing on a neutron star. If you could, its gravity would be so immense, you'd be flattened into a sheet of the atoms, indistinguishable from the surface itself. It would be an instant, violent, unimaginable end. These aren't just objects. They're extreme laboratories of physics. They're terrifying in their power, awe-inspiring in their existence. They remind us that our understanding of reality is constantly being stretched, challenged, and utterly blown away. We thought stars were just giant versions of our sun. We were wrong. We thought death was the end. We were wrong. The universe just keeps getting weirder, more beautiful, and far, far more dangerous. We are tiny, insignificant observers in this cosmic arena, lucky enough to witness the reign of these stellar kings. Their lives, their deaths, their incredible remnants, they carve out the very fabric of the universe, forging new elements, seeding new worlds. But what happens when even a neutron star isn't the end? What happens when gravity wins, completely, utterly? When an object becomes so dense, so powerful, that nothing, not even light itself, can escape its grasp? The universe has a final, ultimate monster, a beast that devours everything in its path, warping space and time around it. And next, we're going to hunt it. The universe just keeps getting weirder, more beautiful, and far, far more dangerous. We are tiny, insignificant observers in this cosmic arena, lucky enough to witness the reign of these stellar kings. Their lives, their deaths, their incredible remnants, they carve out the very fabric of the universe, forging new elements, seeding new worlds. But what happens when even a neutron star isn't the end? What happens when gravity wins, completely, utterly? When an object becomes so dense, so powerful, that nothing, not even light itself, can escape its grasp? The universe has a final, ultimate monster, a beast that devours everything in its path, warping space and time around it. And next, we're going to hunt it. We're talking about black holes, the universe's ultimate predators, not just cosmic vacuum cleaners, but cosmic architects, reshaping galaxies, challenging our very understanding of reality. For centuries, these objects were just mathematical quirks, theoretical impossibilities. But then, we found them. And what we found, it's enough to make your heart pound. Imagine the most massive star you can think of. One that lived fast, burned bright, and then, in its dying throes, collapsed in on itself, not just a little, not just to a neutron star, but to an infinitely dense point, a singularity. The gravity is so intense, so all-consuming, that it punches a hole, a rip in the very fabric of space and time. This isn't science fiction anymore. This is science fact. These stellar mass black holes, born from the death of colossal stars, are our first encounter with the true abyss. They might only be a few times the mass of our sun, but their density, that's where the terror truly begins. Imagine taking something with the mass of Mount Everest and squeezing it down to the size of a single grain of sand. That's what a neutron star does. Now, take something 20 times the mass of our sun and squeeze it down to a sphere just a few miles across, so dense, so unfathomably heavy, that its gravitational pull is inescapable. That's a stellar mass black hole. It's like staring into a bottomless well, where the water flows in one direction only, down. You see nothing, because nothing, not even light, has enough speed to climb out of its gravity well once it crosses a certain boundary. We call that boundary the event horizon. It's not a physical surface, you understand. It's a point of no return, a cosmic threshold beyond which the laws of physics as we know them begin to unravel. It's a one-way door to, well, we don't really know. That's the scariest part, isn't it? The unknown. But these stellar mass monsters, as terrifying as they are just the babies of the black hole family. Because for every stellar mass black hole, there's something far, far grander, far more ancient, lurking at the heart of nearly every galaxy, including our own. For years, Astronomers suspected something huge, something invisible, was pulling the strings at the center of the Milky Way. Stars were orbiting nothing, whipping around an unseen point with impossible speed. The math just didn't add up for any visible object. It took decades of painstaking observations, peering through the cosmic dust that obscured our galactic core, before scientists like Andrea Ghez and Reinhard Genzel finally confirmed it. A supermassive black hole, Sagittarius A, or Sagittarius for short. Sagittarius A is a monster 4 million times the mass of our Sun. Let that sink in. 4 million suns, crushed down into an object whose event horizon is roughly the size of Mercury's orbit. That's big. But here's the thing. It's relatively quiet. It's like a sleeping dragon, occasionally stirring, taking a bite out of a gas cloud, or a stray star that wanders too close, but mostly just existing, a silent gravitational anchor for our entire galaxy. It holds billions of stars in its grasp, including our own Sun, orbiting this invisible behemoth once every 230 million years. You're riding on the back of a cosmic whale, and the whale is orbiting a beast that could swallow us whole without even noticing. Now let's talk about what happens if you get too close to one of these things. If you were to cross the event horizon of a stellar mass black hole, say, one with 10 times the mass of our Sun, you'd be in for a truly terrifying experience. As you approached, the gravity pulling on your feet would be so much stronger than the gravity pulling on your head that you'd be stretched like spaghetti. Astronomers even have a name for it: spaghettification. Your body, your ship, even individual atoms would be torn apart, pulled into long, thin strands, destined for the singularity at the heart of the black hole. It's a death unlike any other, a complete and utter unmaking. It is the ultimate cosmic horror. But for a supermassive black hole, like CGRA, the event horizon is so much larger that the gravitational gradient isn't quite as severe. You might actually cross the event horizon without feeling the immediate rip of spaghettification. You'd pass the point of no return, still intact, still observing the universe outside, for a brief, horrifying moment. But then, as you plummeted deeper, the singularity would become an inescapable truth, and the laws of physics would twist and break around you. What happens at the singularity? We don't know. Our equations break down. It's the ultimate mystery, the edge of our scientific understanding. It's where space and time cease to exist in any way we comprehend. And sometimes these black holes aren't just quiet giants. Sometimes they're feeding. When matter, gas, dust, stars, gets too close, it doesn't just fall straight in. It forms a swirling, superheated disk around the black hole, an accretion disk. This disk is a maelstrom of destruction, where atoms are ripped apart, heated to millions of degrees, glowing with such intensity that they emit X-rays and even gamma rays. These accretion disks can be the brightest objects in the entire universe. Paradoxically, because of the black hole's destructive power, they're cosmic beacons of ultimate annihilation. But Jawir Etion is still relatively modest. It's like a small-town lake monster compared to the true leviathans of the deep, because there's a black hole out there that makes SGRAOX look like a pebble. A monster so unfathomably huge, so terrifyingly massive, that it pushes the boundaries of our imagination to their absolute breaking point. Its name is TON 618, and it's not just a supermassive black hole. It's an ultramassive black hole. This cosmic titan is located in a distant galaxy, 10.4 billion light-years away. And get this, it has a mass of 66 billion suns. Let me say that again. 66 billion times the mass of our Sun. To put that into perspective, our entire solar system, the Sun, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, the Kuiper Belt, even the distant Oort cloud, which stretches halfway to the nearest star, would fit comfortably inside its event horizon. Imagine our home, our entire cosmic neighborhood, existing within the inescapable grasp of this single object. We would be specks of dust, tiny motes, orbiting within its vast, lightless interior, utterly unaware of the inferno that once raged just beyond its event horizon. TON 618 isn't just big. It's a gaping maw, a cosmic horror that defies all scale. Its event horizon alone is 11 times the diameter of Neptune's orbit. If our sun were at its center, Neptune would be orbiting deep inside the black hole itself. This isn't just a place where gravity is strong. It's a place where gravity is reality. It warps space-time itself into a funhouse mirror, twisting light, devouring everything it touches. And remember those accretion disks? TON 618's accretion disk is so bright, so violently energetic, that it makes this ultra-massive black hole one of the most luminous objects ever observed in the universe. It's a quasar, a beacon of destruction that outshines entire galaxies. This monster isn't just passively waiting. It's actively feeding, ripping apart stars, gas, and entire cosmic clouds, spewing out jets of plasma, thousands of light-years long. It's a cosmic engine of unthinkable power, fueled by the ultimate act of consumption. These aren't just objects in the sky. They are cosmic titans, fundamental forces that shape the very structure of the universe. They remind us of our profound smallness, our existential fragility, in the face of such raw, unbridled power. We have traveled from our tiny blue marble, past stellar giants, through the graveyard of stars, and now we stand at the edge of the ultimate abyss. We've peered into the maw of the black hole, and the abyss, it stares back. But what if these aren't the biggest? What if, beyond our current observations, beyond the limits of our telescopes, there are even more unfathomable voids, even greater monsters lurking in the cosmic shadows? What other secrets do these ultimate gravitational prisons hold? And what does it mean for us, tiny, fragile observers on a pale blue dot, to exist in a universe ruled by such magnificent, terrifying titans? The hunt, my friends, is far from over. We've journeyed to the furthest reaches of our imagination, past stars that dwarf our sun, past black holes that could swallow entire solar systems whole. We've faced the cosmic titans, the universe's truly terrifying monsters. And as we stared into their unfathomable depths, we felt a profound, humbling smallness. But what if that feeling of insignificance isn't the whole story? What if, out there, among those swirling nebulae and distant galaxies, there's another kind of monster? A monster of loneliness? The monster of wondering. Are we truly alone? This question, perhaps the most profound humanity has ever asked, echoes through the void. We've seen the sheer mind-bending scale of the cosmos. Now, let's consider its potential for life. Here on our own pale blue dot, life isn't just thriving, it's stubborn. It's tenacious. It claws its way into places we once thought utterly uninhabitable. Think about it. Boiling vents on the ocean floor, where superheated water spews out chemicals that would dissolve you in an instant. Yet, entire ecosystems flourish there, teeming with bizarre, alien-looking creatures, or ice-locked lakes, miles beneath Antarctic glaciers, cut off from sunlight for millions of years, holding microscopic organisms that have found a way to survive on the barest whisper of energy. Even within nuclear waste sites, scientists have found bacteria that eat radiation. These are Earth's extremophiles, and they challenge everything we thought we knew about what life needs to take hold. If life can cling to existence in such hellish corners of our planet, imagine the possibilities out there. For centuries, our search for extraterrestrial life was pure speculation, confined to the pages of science fiction. We had no way to know if other suns had planets at all, let alone planets that might harbor life. Then, in the mid-1990s, everything changed. We discovered the first exoplanets, planets orbiting stars beyond our own sun. At first, they were just a trickle, then a stream, and now, a flood. We've found thousands, and with every new discovery, our understanding of the universe shifts. We now know that planets aren't rare cosmic accidents. They're the norm. Most stars, perhaps even all stars, have planets. Think about that for a second. Every single star you see twinkling in the night sky, from the closest to the most distant pinprick of light, is likely a sun to its own collection of worlds. And many of these worlds exist in what we call the habitable zones, the Goldilocks region around a star, where temperatures are just right for liquid water to exist on a planet's surface. Not too hot, not too cold, just right. We've found super-Earths, mini-Neptunes, and even rocky worlds roughly our size, orbiting red dwarf stars that glow for trillions of years. Imagine the immense spans of time life would have to evolve on such worlds. The numbers are staggering. Our Milky Way galaxy alone is home to hundreds of billions of stars. If even a tiny fraction of those stars host a planet in the habitable zone, we're talking about billions of potentially life-sustaining worlds just in our cosmic neighborhood. Billions. That's more than all the grains of sand on all the beaches of Earth. So, if the universe is brimming with potential homes for life, why haven't we heard from anyone? This is the core of the Fermi paradox, a question that has haunted scientists for decades. Where is everybody? To try and grapple with this, we turn to something called the Drake equation. It's not a formula to give you a definitive answer, but rather a framework, a way to organize our ignorance. It's a series of probabilities, multiplied together, that attempts to estimate the number of intelligent, communicating civilizations in our galaxy. It starts with the rate of star formation in our galaxy. We know that. Then, the fraction of those stars that have planets. We're getting better at estimating that. Next, the average number of planets per star that can potentially support life. Again, our exoplanet discoveries are shining a light here. But then, the variables get squishier. What fraction of those habitable planets actually develop life? What fraction of that life goes on to evolve intelligence? And then, what fraction of those intelligent civilizations develop technology capable of interstellar communication? And finally, how long do they last? Each of these factors is a massive unknown, a cosmic roll of the dice. But even with conservative estimates, the Drake equation often suggests that our galaxy should be teeming with intelligent life. Yet, we detect nothing. Silence. This silence is profound. It's the universe's most chilling whisper. What explains it? Maybe life is incredibly rare, a fluke that only happened here. Maybe intelligent life is common, but it never develops the technology to communicate. Or maybe, and this is the truly unsettling thought, there's a caput or great filtering, some insurmountable obstacle that prevents intelligent civilizations from reaching a certain point. Perhaps that filter is behind us. An early hurdle life on Earth somehow miraculously overcame. Or perhaps it lies ahead. A technological singularity, a self-inflicted ecological catastrophe, an interstellar war, or a cosmic event we can't even conceive of. The thought that an advanced civilization might be inherently unstable, destined to destroy itself before it can spread amongst the stars, is a sobering one. It makes you wonder about our own future. Despite the silence, the search continues. For decades, dedicated scientists and engineers have been running projects like SETI, the search for extraterrestrial intelligence. They are not looking for little green men with ray guns. They're listening. They're pointing massive radio telescopes at distant star systems, hoping to pick up a signal, a coded message, a flicker of intelligence amidst the cosmic static. It's like standing on a vast, empty beach, straining to hear a single seashell whisper across the roaring ocean. It's a testament to human hope, to our innate desire for connection. Imagine what that first signal would mean. It wouldn't just be a scientific discovery. It would be a revolution. It would fundamentally alter our understanding of our place in the universe, our very identity. We would no longer be alone. We would be part of a grand cosmic tapestry of life. But until that day, we're left with the magnificent, terrifying silence. It's a silence that forces us to look inward, to appreciate the precious, fragile miracle of life on Earth. It reminds us that our unique perspective, our consciousness, our ability to even ask these questions, is a profound gift. The universe has shown us its terrifying giants, its cosmic monsters of mass and energy. But perhaps the greatest mystery, the most awe-inspiring unknown, isn't about size at all. It's about life. It's about company. It's about whether, somewhere out there, another pair of eyes is gazing at their own night sky, asking the very same question, hoping for an answer, a whisper in the dark. The search continues, and what we discover, or don't discover, will define our cosmic destiny. What if the universe has been trying to tell us something all along? What if the message isn't out there, but right here, waiting to be understood? It's a powerful thought, isn't it? The universe, a vast silent ocean, and we tiny boats adrift, scanning the horizon for a distant shore. We've chased the echoes of creation, peered into the hearts of collapsing stars, and stood awestruck before the cosmic monsters, those titanic forces that warp space and time. We've measured their terrifying scales, marveled at their raw power, and felt our own insignificances in their shadow. But there's another monster, perhaps the most terrifying of all, not because of its size or its immediate threat, but because of its inevitability, time itself. And with it, the ultimate end of everything we know. Every story, no matter how epic, has a final chapter. Every star, no matter how brilliant, eventually fades. Even the grand, sprawling narrative of our universe, a tale spanning billions of years, seems destined for a conclusion. It's a thought that can stop you cold, can make the very ground beneath your feet feel a little less solid. We've been looking outward, searching for life, for answers, for companionship. But what if the deepest truth lies not in what is, but in what will be? What if the universe has been telling us a story about its own final moments all along? Scientists, those tireless cosmic detectives, have pieced together several possible endings for this grand cosmic drama. They're not pretty. They're not comforting. But they are, in their own terrifying way, profoundly beautiful in their scale and their finality. They are the universe's swan song, written in the language of physics. The leading theory, the one most cosmologists are betting on, is something called the Big Freeze, or heat death. Imagine a boundless, ever-expanding ocean. Our universe is that ocean, and it's getting bigger, faster all the time. As it expands, everything gets further apart, everything gets colder. The energy that fuels stars, that powers galaxies, that makes life possible, it all gets spread thinner and thinner, like butter scraped across an infinite piece of toast. Stars, those brilliant cosmic furnaces, will eventually run out of fuel. They'll dim, they'll sputter, they'll go out one by one, until the night sky, once a glittering tapestry of light, becomes an inky, eternal black. This isn't a sudden catastrophe. This is a slow, agonizing fade, a cosmic twilight that stretches for trillions upon trillions of years. Imagine the last star in the universe, a tiny red dwarf, burning with the faintest embers of its life, millions of times longer than our sun has even existed. And then, it too, winks out. What's left? Black holes. Those very same cosmic monsters we've been hunting. They'll become the last titans standing. They'll slowly, imperceptibly, devour anything that gets close. But even black holes aren't immortal. Thanks to a bizarre quantum phenomenon called Hawking radiation, they too will eventually evaporate, slowly, patiently, over timescales so vast, so utterly incomprehensible, that our entire universe's current age is less than the blink of an eye in comparison. The largest black holes could take quadrillions of years to vanish. Think about that. A single solitary black hole, quietly fading into nothingness, long after every star has died, long after every galaxy has dispersed, long after every atom has drifted apart. And then, nothing. Just a cold, empty void. A diffuse soup of photons and subatomic particles, so spread out, they rarely interact. No energy to do anything. No stars to warm anything. No light, no heat, no movement. Just an endless, uniform, freezing dark. The ultimate quiet. The universe, having played out its magnificent symphony, will finally fall silent. It's a chilling prospect, isn't it? A universe destined to end not with a bang, but with the quietest, most desolate whimper imaginable. But what if it's even more violent? What if the expansion of space doesn't just spread things out, but actively rips them apart? This is the Big Rip. Imagine that same expanding ocean. But now, the expansion is accelerating so ferociously that it starts to tear at the fabric of existence itself. First, galaxies are pulled apart. Then, solar systems. Then, planets. Eventually, the very atoms that make up our bodies, the forces that hold them together, even those succumb to the unstoppable tearing of space. It's like unwinding a sweater, thread by thread, until there's nothing left but individual fibers. Then those fibers get ripped into nothing. In this scenario, the end isn't a slow fade. It's an apocalyptic sprint, a sudden violent unraveling where everything, every star, every black hole, every particle, every thought, is torn into a million pieces in a final agonizing cosmic scream. A universe that simply stops existing because its very structure has been annihilated. Thankfully, current observations suggest the Big Rip isn't our fate, at least not for many, many billions of years. But the possibility still hangs there, a terrifying alternative. There are other, less favored ideas, like the Big Crunch, where the universe's expansion reverses, drawing everything back into a fiery, cataclysmic recollapse. A cosmic rewind to the beginning, perhaps to spark another Big Bang. A cyclical universe, born anew from its own ashes. But evidence for this has largely faded. For now, the cold, silent fade of the Big Freeze seems the most likely cosmic destiny. So, where does that leave us? We, these tiny, fragile beings, living on a small blue marble, orbiting a middling star, in a vast, indifferent cosmos. We've spent our existence building, creating, loving, striving, discovering. And all of it, ultimately, destined for the same cold, quiet end. It's a thought that can bring a profound melancholy, a sense of cosmic futility. What's the point of it all, if it's all going to end anyway? But here's where the story pivots. Here's where the fear of the end transforms into something truly profound. Because while our physical presence is fleeting, our legacy isn't written in stone or stars. It's written in consciousness, in understanding, in stories. Think about it. We are the universe, gazing back at itself. We are the fleeting, improbable spark of awareness that can even comprehend these vast scales, these terrifying endings. We are the ones who have named the cosmic monsters, charted their movements, and dared to ask how it all began and how it will all end. No black hole, no supergiant star, no swirling galaxy possesses this ability. They simply are. But we know. And that knowing, that capacity for wonder and awe, is our most extraordinary gift. Our universe is ancient, stretching back nearly 14 billion years, and it has billions, perhaps trillions more years to go. Our existence, the entire span of human civilization, is less than a breath in that cosmic epic, a mere nanosecond. And yet, in that nanosecond, we have done something truly miraculous. We have pulled back the curtain. We have begun to understand the script. We have not just witnessed the cosmic ballet. We have started to decipher its choreography. Every equation scribbled on a blackboard, every telescope aimed at the dark, every story shared around a campfire, every piece of art inspired by the night sky. These are our enduring monuments. They are our legacy, not against the inevitable end, but within it. We may not stop the big freeze or avert the big rip, but we are the ones who get to tell the story of it all. We are the universe's own consciousness, its memory, its voice. That's why those cosmic monsters, those terrifyingly large objects, aren't just sources of fear. They are sources of profound awe. They are the punctuation marks in the universe's grand narrative. They remind us of the immense forces at play, forces that sculpted galaxies and birthed stars. And by understanding them, by placing ourselves in context with them, we elevate our own existence. We turn fear into wonder, insignificance into purpose. We, humanity, are the universe's fleeting dream. We are the consciousness that emerged from the stardust, gazed upon the stardust, and began to understand the stardust. Our ability to ask why and how and what next is a testament to the incredible, improbable journey of life itself. We are the storytellers, and our story is one of curiosity, resilience, and an unyielding drive to know. So when you look up at the night sky, don't just see the distant pinpricks of light. See the legacy, see the story. See the cosmic monsters, not as threats, but as chapters in an unfolding epic that we are lucky enough to witness, and even luckier enough to narrate. Yes, the universe is vast, and we are small. Yes, time is relentless, and our moment is brief. But in that brevity, in that smallness, lies our greatest power, the power to comprehend, to appreciate, to marvel, and to inspire. Our legacy won't be in the monuments we build, which will crumble. It won't be in the technology we create, which will rust. Our legacy will be in the understanding we forge, the stories we tell, and the wonder we share. It will be in the echoes of our questions, whispered across the eons, long after our planet is gone, long after our sun has died. It will be in the fact that, for a precious, fleeting moment, the universe woke up. It saw itself. It understood its beginning and its end. And it was beautiful. Cherish this moment. Cherish the starlight that falls on your face. Cherish the questions that stir your soul. Because we are here now, in this brief, brilliant flicker of cosmic consciousness. We are the universe's grand finale, not in its physical end, but in its self-awareness. Let us continue to look up. Let us continue to explore. Let us continue to dream, because in doing so, we don't just exist. We become the universe's enduring song. And what a magnificent song it is.